Welcome everyone. Today we're going to dive into a fundamental concept in computer science, hashing in data structures. This presentation is designed as a complete beginner's guide to help you understand how it works, why it is so important, and how it is applied in technology we use in every day. To truly understand hashing, let's start with a simple library analogy. Imagine you walk into a massive library containing 1 million books. If you need to find a specific book, how would you do it? Option A is having no system at all. You would walk aisle by aisle, checking into each shelf, which could take days. Option B is having an index system. You could go to a catalog, look up the book, get an exact shelf number, and go directly there in seconds. For computer data, hashing is like option B. So, what exactly is hashing? A simple definition is that hashing is a technique that maps large amounts of data to a small fixed size value using a special function. The real technical definition is that it's a process that converts a given key into another value. A hash function is used to generate this new value according to to a mathematical algorithm. Think of it as creating a digital fingerprint for your data. Why do we need this? Without hashing, searching for data in a large collection would require checking each and every element, which takes linear time or O of n time. With hashing, we can find data almost instantly in constant time or O1 time. With Let's directly compare the two approaches. Without hashing, retrieval is slow because the computer checks every element. O of n with hashing, it is fast because you have direct access to items. O of 1. While both methods store data, they differ significantly in their lookup cost. Let's look at another everyday example. When you log into a website, does it actually store your password? No. It stores the hash of your password for security. This is powered by functions, which are mathematical formulas that take an input like the name John and produce a fixed size output like a number. Here's a visual of how a hash function maps data. The central mapping process takes an input string and gives an output. For instance, if the input is John, it might run through the hash function and output the number 42. The input string Sarah might output 87 and Mike might output 13. Properties of a good hash function. Not all hash functions are created equal. A good hash function has five key properties. First, it must be deterministic, meaning the same input must always produce the same output. John will always be 42 and never 43. Second, it has a fixed output size. So whether you hash a single letter or an entire book, the output size is the same. Third, it must be efficient and fast to compute. Fourth, it should have a uniform distribution, spreading inputs evenly across all possible outputs. Finally, it needs the avalanche effect, where a tiny change in the produces a completely different hash. Here are a few common ways we calculate these hash mathematically. The division method uses the formula h key equal to key modulus the table size. For example, if your table size is 10, key 53 goes to position 3. The mid square method involves squaring the key and extracting the middle digits. For a key of 50, the square is 2500 and the middle digits are 50, leading to the position 50. Digit folding splits the key into parts and adds them together. For example, a key of 1, 2, 3, 4, 5, 6 splits into 1, 2, then 3, 4, and 5, 6, adding up to 102. The position is then 102 modulo the table size. So, what is a collision? Now, returning to our library analogy, what if two different books get the exact same shelf number? If the hash of John is 42 and the hash of Jane is also 42, we have what is known as a collision. By definition, collision is when two different inputs produce the same hash output. Think of it like parking spots. You might have 10 parking spots representing a hash table, but 100 cars representing possible inputs. Multiple cars must share spots. When input strings Jane and John both map to output 42, we need a way to resolve it. One collision resolution technique is separate chaining. The concept is that each hash table position holds a linked list, and when collisions happen, we add the new item to the list. So position 40 would look like John, then Jane, then Jack. It's like having multiple books stacked on the same shelf. You can still find them, you just have to look through the stack. The pros are that it's simple to implement, allows unlimited items per position, and is good for frequently inserted or deleted data. The cons are the memory overhead for pointers, and in the worst case, where all items land in one list, it degrades into a linear search. Another resolution method is the linear probing. The concept here is that if a spot is taken, you try the next spot, then the next, until you find an empty spot. For example, if Jane wants position 42, but 42 is taken by John and 43 is taken by Sarah, we place Jane in position 44 because it's empty. It's like finding a seat in a crowded theater. If your favorite seat is taken, you take the next available one. The pros are that it requires no extra memory for pointers and is cache friendly since memory is sequential. However, the cons include the clustering problem, where consecutive spots get filled, making deletion tricky. Other methods and types of hashing. Other collision methods exist, such as quadratic probing, where instead of checking spaces linearly by plus 1, plus 2, plus 3, we check plus 1 squared, plus 2 squared, and plus 3 squared. For position 42, we try hashing, then 46, then 51. This reduces clustering compared to linear probing. Double hashing uses a second hash function to determine the step size if the first spot is taken. This distributes items more evenly and reduces clustering significantly. There are also four main types of hashing. Static hashing has a fixed table size used when you know exactly how many items you'll store. Dynamic hashing grows or shrinks as need for unpredictable data sizes. Cryptographic hashing is used for security and acts as a one-way function used in password and blockchain. Finally, perfect hashing creates a function with no collisions for a known fixed set of data. Hashing powers the digital world. Websites use it for password storage, storing hashes instead of actual passwords. Databases use hash tables for indexing to find records instantly. Caching systems like Redis store frequently accessed data in hash tables for quick retrieval. Compilers use hash tables to track variable names and their addresses. Bitcoin uses cryptographic hashing to link blocks in the blockchain. It is also used for file integrity checks to ensure a downloaded file wasn't corrupted, and in spell checkers for O1 dictionary lookup. To weigh the pros and cons, the advantages of hashing include speed with O1 average time for search, insert, and delete efficiency for large datasets, security through cryptographic options, flexibility with any type, and space efficiency since it only stores what when you need without extra indices. The limitations are that collisions will always happen with enough data. There is no ordering, so you can't easily traverse data in sorted order or perform range queries easily. Also, there can be memory waste because the table must be larger than the data for efficiency. Resizing a growth table is expensive, and bad hash functions yield poor performances. Let's let's tie it all together with a student record system. We need to store students by their ID numbers in a hash table with 10 positions. Our hash functions will be the ID modulo 10 or the last digit of the ID. We insert student 101 to position 1, student 102 to position 2, and student 103 to the position 3. Student 111 also calculates position 1, causing collision with 101. So what do we do? Using separate chaining, position 1 becomes a linked list containing 101, then 111, then 121. Positions 2 and 3 hold 102 and 103 respectively, while slots 0, 4, and 5 are empty. If you want to search for student 111, we hash 111 to position 1, go to the list and traverse until we find 111. The time complexity is O1 in the best case and ON in the worst case if all items end up in one list. To delete student 102, we hash to position do and simply remove the node. Here we can see the example. Key insights and takeaways. A key insight is that if all keys land in the same bucket, the table is slow. This shows exactly why choosing a good table size and hash function matters. They help spread keys evenly across buckets. To summarize our key takeaways, the core principle of hashing is turning a key into a spot in a table so you can find it quickly. Collisions happen when two keys go to the same spot and we fix them with chaining or probing. Performance relies heavily on a good hash function and table size. There are diverse hashing methods suited for different systems. More importantly, hash tables are fast, efficient, and used everywhere real in real applications. Before we finish, here is a quick reference card covering everything we discussed. Thank you.